Okay, so we were talking last class about the knapsack problem. I've just quickly summarized that problem so we're on the same page. So we had n items. Each item has a weight and a value. And you have a knapsack or backpack, and it has a capacity of capital W. And your objective is to pack your backpack full of items such that you maximize the total value of items in your backpack, right? And you can't exceed the weight capacity of capital W. And we talked about, there's two variants of this problem, knapsack without repetition and knapsack with repetition. We were talking about with repetition right now. And so in it, you can take multiple of each item. So there's a stack of items of each kind, and you can take many of them if you want. And we got down to a dynamic program that looked like this. So K of 0, that stores the maximum value we can obtain with a backpack of capacity 0. And so the maximum capacity or maximum value we can get is 0. And then we just loop through all the possible weights from 1 up to the true capacity of our backpack. And we solve and we have that recursion that says the maximum value you can get with weight W is given by the max over all items I that have a weight less than this W. The best value you can get without that item, plus the value you get adding that item in. Right? So it's like, what's the best solution that contains item I? And it's going to be written as the value of I plus the subproblem of optimally packing the remaining volume in my backpack. And then I do that over all I, right? Take the best option over all I. And so we said this runs in, if you look, the for loop runs capital W times, and in each time we have to take a max potentially over all the items I, there's n items. So it runs in NW time. And I was commenting, but I didn't write it down. So this will just be the last part on this, is that the runtime depends on W. This is the value of the input, not the size or number of bits. So, for example, using M bits, W could be 2 to the M, or 2 to the M minus 1, I guess would be the largest number. And so you can see, even without making my input very large, my runtime, or to say it differently, my runtime grows exponentially in the input size. So this is not a polynomial time algorithm, right? Because the input size is the number of bits I need to represent the input. And this is growing, this W is exponential in the number of bits needed to represent it. So this is not a polynomial time algorithm. Sometimes this is called pseudo-polynomial. Yeah. What does n represent? N is the number of items. Yeah. So if W is not too big, this runs fast, right? And I said this last class, but the only issue is if W is enormous. For example, W is 2 to the power of 100, or even 2 to the power of 64. Let's say we're doing 64-bit integers, right? It's 2 to the power of 64. That's a huge number. And so that for loop running 2 to the 64 times, is never going to terminate on like our personal computers, right? It turns out this problem is hard, this knapsack problem. To solve optimally, it's hard in the same way that when we talked about vertex cover being hard, or kind of like factoring being hard. So it turns out it's not surprising that we get an algorithm that has a runtime that looks like this. Later on, and very last week of the class, we'll talk a bit more about approximation algorithms, and we'll actually come up with a way to kind of come very close to finding the optimal solution in polynomial time, true polynomial time. But that's for later. Okay, so now let's continue. So the other version, oh, sorry. I want to make a note, and then we'll go to Knapsack without repetition. Sorry. So an important thing in dynamic programming is called memoization. So the way we've been talking about dynamic programming so far, we're essentially filling out a table. We start by filling out the smallest subproblem, and then we incrementally fill in successive entries. Right? It's either a big long array where to fill in an entry in the array, we look at prior entries in it, or it's a 2x2 table, right, in the case of edit distance. But you can also implement these algorithms recursively instead of, which is called like a top-down fashion, instead of this bottom-up fashion. And so we can implement using recursion instead of an iterative algorithm. But to avoid the kind of pitfall that we had when we talked about the Fibonacci, computing Fibonacci numbers back in the first lecture, we want to store our answers to subproblems so that we don't repeatedly compute them. Right? That was the thing that sunk our Fibonacci recursive algorithm, is like we calculated over and over and over again. So the idea is to initialize a hash table to hold the values. And every time we compute a new value, k of some weight w, we then store it in the hash table. And the next time we need it, we just look it up from the hash table rather than using that recursion that we had. So for Knapsack, the hash table holds the values kw indexed by the weight w. And the Knapsack algorithm looks very simple. So when we're calling, so we've initialized it outside of Knapsack, this hash table. And then when we're trying to compute for some weight w bar, we first check, is that w bar in our hash table? If it is, then we just return the value from the hash table. Otherwise, we compute it recursively. And so the only interesting thing here is you can see that I'm making a recursive call to my function Knapsack, right? So to compute the value k of w bar, I make a recursive call to my Knapsack, where in each one of those recursive calls, I might just look it up in my hash table. It might be there, right? Or it might not, in which case it'll recursively call itself again. And then after I've got this value, I insert it into my hash table, and then I return. So the runtime of this is big O n times w bar, just the same as the other one, because I do this storing, so I don't ever compute something twice. Typically, if you have the choice between recursion and an iterative algorithm, you're better off with an iterative algorithm. But there is a potential advantage to this idea. And it's that one could think of it as like a lazy method, where I'm only computing a k of w if I'm going to need it. So in the end, I want to get k of capital W, right? And so this recursive call goes down, and it looks up certain k of smaller w's. But in the bottom-up approach, I just fill in every single entry of my table. In the top-down approach, I might skip some entries of the table because it might be that I don't even need those values in order to compute k of capital W. And so that can save us. And just to give you an extreme example, like let's say that all wi's, this is kind of a, maybe too simple example, but all the wi's and our capital W are multiples of 10. Then there's no need to calculate K of 3 or K of 7. I mean, those are just two examples, right? But anything that's not a multiple of 10, there's no need to calculate it. So if I just naively implement the bottom up, I will actually fill in all of those entries in the table. Whereas if I do this top down one, just naturally, it'll only look up the multiples of 10 because all the weights are always going to be multiples of 10. Does that make sense? So this is not specific to Knapsack. I mean, you always have these two options when implementing dynamic programming. You can do bottom up or top down. And there's not, you know, it's not that one is always better than the other. In some sense, it will depend on how many does the top down get to skip. If it ends up filling in the whole table, you will have been better to go bottom up. If it doesn't, then this will be better, right? If it's in skip a lot of entries. And it's hard to know typically, like unless you know something about the structure of your problem. Okay. So now the other version of Knapsack, which is Knapsack without repetition. I call this one the art heist. You know, you go into whatever, the Louvre, and there's one of each painting, right? There's only one Mona Lisa, and you can shove some things into your backpack. So now, why is this different? Why am I distinguishing between with repetition and without repetition? The main reason is that now I have to keep track of what items are already being used in a partial solution, because then that affects what I can add. Like this subproblem that I defined before, K of W minus W, so K of W minus WI isn't helpful because item I might already have been used in this solution here. I don't know, right? So somehow I have to keep track of what items are in the solution and what's the weight that I have available. So the idea for this one is to keep track of the items being used in these partial solutions. And to do this, I'm going to add a second parameter to the subproblems. So using again, this is the hard part about dynamic programming, is coming up with your definition of subproblem. But I'm just going to build on all the ways we've seen for the other problems we've looked at, which is, so the weight idea seemed like a good one. Build up weights, right? Start with a knapsack of weight 0 and go up. But now I also need to keep track of items. So I'm going to introduce a second index, J, which will say, now, what's the best way I can pack my knapsack if it has a capacity of W and I can only use items 1 through J? And now I can think of to compute a bigger subproblem, it'll be like, what if now I'm also allowed to use item J plus 1? Maybe with the same weight, right? Or otherwise I could say I have the same set of items available and now I have a bit more weight that I can use in my backpack. But that's going to be my new subproblem definition. So K of Wj equals the max value I can attain with capacity. How about I write a bar over the W so we can tell that it's not my capital W, with a capacity W bar and items 1, 2, up to J. So I don't have to use all those items, right? It's just like, that's my universe of items. It's just the ones 1 through J. So if this is my definition of subproblem, let's suppose I filled all these out. It's a big table, right? Now, what's the actual answer? If I had, solve, like, given that I filled out this table, what's the solution to the knapsack problem? Which entry should I be returning? Yeah. Yeah, yeah. The big W, right? And all N items. So answer to the problem is K of W and N. So next, how do we express this in terms of smaller subproblems? So there's maybe two cases to split it into. Let's look at like the last item J, that's, you know, the highest index. If that one weighs more than W, then I know it's not in my solution. Right? And so then the solution to this subproblem is just the same as the solution to W, comma, J minus 1. Because J was too heavy to even fit in my backpack with capacity lowercase w. So if Wj weighs more than what I have available, then K of Wj equals K of Wj minus 1. Otherwise, if it fits, if item J fits, then what happens? So we've got, I think we've got two options in this case. One is I don't use item J in my solution, right? Even if it's available. So in that case, I just get, if I'm not using it, then the solution to Wj is the same as the solution to Wj minus 1. The other option is I do use it. If I use it, then I get the value of it, which is Vj. And then what's left over? Well, it's going to be the subproblem, W minus the weight of that item. And the remainder of my backpack has to be filled with the other items, which is 1 through J minus 1, because I've now used J in my solution. I can't use it again. So this is if we don't use J. And this one is if we do use J. Yeah. That's right. Yeah. So the question was, are we just using the first J? Yeah. So let's just say that items are numbered from 1 to N. And we really mean we're just going to use items 1, 2, 3 up to J. So it's kind of arbitrary, right? Because, yeah. Okay. So then the other thing, I mean, one thing maybe you already noticed, right, is this subproblem is like the recursion here is a little bit simpler than what it was in the case, sorry, I was good, in the case with repetition. Because now I'm only, to fill in that entry, I only have to look at 2 others. In the previous one, I had to take a max over all the i's, right, that had a weight less than W. But now that came at the expense of now I have 2 indices in my subproblems. So my table is big, right? Like my memory now is larger, but my work to fill in an entry is smaller. So what are the smallest subproblems? They're always going to be these, you know, the ones where I let the indices be 0s or 1s, you know, like the smallest values. And so let's think about this one. I have a backpack of capacity W, and I'm allowed to use no items. What's the value I can obtain? 0, right? And the other is equally easy to think about. So I have my backpack can't hold anything, and I have items 1 through J to consider. Again, nothing, right? I can't fit anything in my backpack. Assuming all items have positive weight, which is when this problem makes sense. Okay. Oh, what in? Oh, I see. Sorry. I'll have to fix this after. You can see I made like a section heading for memoization, and then we like left memoization. We're now within Knapsack without repetition, but the header memoization is continuing down. Sorry, it's just I'll fix that after. But I was just getting confused. I was like, how did we return to memoization? Yeah.
We also have to consider like if we have weight left over, but we used all the items.
If you have, there's nothing you can do in that case. Like your question was, if you have weight left over, but you've used all the items, but then that's just the best solution, right? When J is 0. Yeah. I think this is enough to fill it in, because now if you look at my recursion, we've got the initialization, right, in line 1. And now we've got a nested for loop, because we have to go over, increase the items we're considering and increase the weight or the capacity of our backpack. And then we just do the check, right? The 2 cases. 1, if the new item we're considering, J, can't fit in our backpack, then the subproblem is just the previous one. Otherwise, we compute the max of the 2 possibilities, right? Which is exactly what I wrote above. This one is if I don't use item J, and this one is if I do use item J in this solution. And then at the end, I just return my final answer, right? Using the full capacity of the backpack and all of the items. So what is the runtime of this algorithm? Yeah. Okay, so if I just look at lines 2 through 7, like that's where all our work is being done, right? So what do you think the runtime of it is? Thing is still like, I mean, I've got these nested for loops. It's going to go through every option, right? It'll start with J as 1 and then loop from W is 1 up to capital W. Then it'll increment J to 2 and it'll do the same thing again. So once I see these nested for loops, necessarily I'm already going to be spending N times W iterations. And now the question is like, what's in lines 4 through 7, right? Like what's the work per iteration? And in this case, it's just constant time, because I evaluate an if statement, order 1, and then in the else, it's just a max of 2 values. They're all stored in a table, so that's just order 1 as well, right? So this is, oops, this part is order 1 per iteration. And then you can see we have NW iterations. Big O N times W time. And like I said, so they have the same runtime. The only meaningful difference in this is which we don't talk about this very much in this class, but is that what we call the space complexity, which is how much memory we use to run this algorithm. This one has to fill out an n times w table. So its space complexity would be big O n times w. The previous one only had to fill out a table of size w, right? Or it was like a list, an array, because the subproblems were just k of a single index w. So it had a space complexity of big O of w. So same runtime, but they use different amounts of memory. This one uses considerably more memory, which can be an issue, right? I mean, if W is 100 million and N is 100, that's not going to be great on your memory, right? Okay, so runtime for Knapsack without repetition is big O n times W. Any other questions on Knapsack before? I've got one more example, which is all pairs shortest paths. Kind of our final revisit of shortest paths in graphs. Well, kind of. Actually, we'll sort of talk about more complicated versions in when we get to complexity theory. But no, we're good. Okay, so all pairs shortest paths is the problem that's as it sounds. I have a graph and I want to basically compute a two-dimensional matrix where the ijth entry contains the shortest path from vertex I to vertex j. Right? Dijkstra's algorithm, or all the ones we've thought of so far, they take in a start vertex and they compute the shortest path to all destinations. Same with Bellman-Ford, right? And so that's the main difference here. We're also going to consider it in the case where the edge lengths could be negative, but there's no negative cycles in the graph. So edge lengths could be negative, but no negative cycles. If you remember, our algorithm for that was Bellman-Ford. Dijkstra's required positive edge lengths. And it had a runtime of big O V times E. We could definitely use that to solve this problem, just call it on every start. Right, so the algorithm, I mean, I'll write it, but it's pretty straightforward. It's just for each V in V, shortest paths, that was what we called the algorithm, GLV. That's it. I mean, I guess I should keep, maybe the output for this one is going to be, it's an array of distances, so I call that dist V, right? And then I get the next start and I get another array, right? Just I should save all the arrays and then stack them to make my matrix. Yes?
This might be like general.
Yeah, that would help. I think that's a good question, actually. So I'm not entirely sure. Yeah. So the question, I mean, if the video version of this, the question is just if you have negative cycles, but you added the restriction that you can only visit each vertex once, then I think the shortest path problem is still well defined. I don't actually know what the correct algorithm is in that case. I'd have to think about what. It's also less clear what the meaning of it is, I guess, like, why we're adding in that restriction still. Like what practical problem are we solving where we kind of are enforcing no double visits to a vertex? But it's an interesting question, yeah. So this will run in big O E times V squared time, right? Because the Bellman-Ford ran in V times E and we do it V times. So the question is, can we do better? The answer is going to be yes, but we're going to use dynamic programming to do it. And this is a clever algorithm. I would say it's not easy to come up with these subproblems on your own, although it follows in the exact same pattern that we've been doing. So what do we want to do? We want to compute dist from I to j for all pairs ij. Now, in dynamic programming, we have to we want to make a subproblem, right? And we want to limit something to make that problem easier. The way we limit it, I think, is not totally obvious, although it does follow the pattern. So the way we're going to do it is say, what's the shortest path that takes me from I to j, where for intermediate vertices on that path, any ones that appear between I and j on the path, I'm only allowed to use vertices 1 through k. So like I got I and j, and then in between, right, there's going to be some vertices. And for those, I'm only allowed to use a subset of all the vertices in the graph. And those are going to be the ones 1 through k. So it's going to be a 3-index subproblem. And I'll say, I mean, this algorithm is called Floyd-Warshall that we're describing here. It's Floyd and Warshall got their names on it. So if it was totally obvious for all of us immediately how to define the subproblems, they probably wouldn't have their name attached to it, right? Like there was some insight they had in it that made us acknowledge them. So it's going to be so I'm going to write a dist from I to j using items or vertices 1 through k. And it has a long definition, which is shortest path from I to j where intermediate vertices can come, or how about can only be in 1 through k. I say intermediate vertices because the endpoints I and j might be larger than k. It's just everything in between them on the shortest path has to be between 1 and k. And so then the answers are going to be dist I, j, and the number of vertices, which we usually call n. So how do I relate subproblems to smaller subproblems in this case? The idea is going to be, okay, if I want to fill in, let's say, well, if I want to fill in dist I, j, k plus 1, how do I do it in terms of, let's say, dist I, j, and k? Right? I get one extra vertex, k plus 1, let's say, that I could use on my shortest path between I and j. So I have to decide whether or not to use it, basically. So the picture, I think, really helps in this case, which is I've got vertex I, and then over here, I've got vertex j. And I have a new vertex, k plus 1, that I could use on my shortest path from I to j. And the current best shortest path I have is something down here, which has a length of dist from I to j using vertices 1 through k. Like, you know, a subset of those vertices. And now I have this new one, right? So my new path either continues to use that. Now that I can use k plus 1, it either doesn't use it or it does. If it does use it, then it's got to take a shortest path to get to k plus 1. And it's got to, again, use a shortest path to get from k plus 1 to j. Because we know like subpaths of shortest paths are also shortest paths, right? So let me draw these two things, and then let's see if we can label what the distances are on these. So this is like my second option. So this one here is kind of like my current best. And then this one up here is like my new option. And this dist here is going to be, I'm going from I to k plus 1. And what vertices, what should be this third argument here? Yeah. Yeah. And you're not going to use it again, right? Like if you're trying to get from AI to k plus 1, you're not going to visit k plus 1 in the middle. You would have already got there then, right? So this is only going to use vertices 1 through k. And then here I'm going from k plus 1 to j. And again, it's only using 1 through k. And so then my shortest path from I to j using the vertices 1 through k plus 1 is just the better of these two options. So it's the min of I don't use vertex k plus 1, or I do. If I do, it's the sum of the two red edges. Right, so I go dist I to k plus 1 using k, 1 through k, plus the dist from k plus 1 to j using vertices 1 through k. This one is don't use k plus 1 in my shortest path. This one is I do use k plus 1. Yeah. Say that again. I just couldn't quite hear. No, they can be any, like, so for example, like I could be vertex 3, j could be vertex 12, and k could be 4. So then it's like, what's the shortest, I forget even the numbers I just said, but what's the shortest path from 3, I forget what I said, to 12, where in between I can only use the vertices 1, 2, and 3. Or 1, 2, 3, 4. Yeah. It would always be all of them up to k, right? 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and so on. So sometimes there might not be a solution even, right? There might be no way to get from 3 to 12 using only intermediate vertices 1 and 2. Because it depends whether or not those edges are even in the graph, right? But that's fine. We just fill those in as infinities. So let's do the smallest sub. Let's just wrap this up because we're almost done, and then we'll take a decent break, and then we'll continue on the next section. So, because we're very close. So, smallest subproblems, we just limit k to be 0, right? I mean, that's the way we always kind of do it. Is the I and j aren't really like indices in our subproblems. They're like, that's one of the solutions I want to get. I want to get dist ij for all pairs ij. So our dist ij, and I'm not allowed to use anything in between. What's the solution to this going to be? Yeah. Exactly. Yeah. So if I have an edge directly from I to j, then it's just going to be Lij. So if ij is in my edge set, and it's infinity if ij, like, I mean, it's just otherwise, right? But it's infinity if it's not in my edge set. And then that, yeah. K is the vertex. So maybe let me draw one more picture up here. So it could be, for example, let's say this is my graph. So a subproblem then could be, I want to go from I to J, from 1 to 5, and in between, of all the vertices in between, I'm only allowed to use those that are, let's say, 1 or 2. So this is K equals 2. That means I'm only allowed to use on the shortest path to get me from 1 to 5. In between, I can only use 1 or 2, or both of them. And so in this case, there's actually no solution, right? There's no way, I need to get up to use 1, 2, 3. So those are the subproblems. And so ij0 means I'm not allowed to use anything in between. I have to go directly from 1 to 5. Okay, so this then gives us our Floyd-Warshall algorithm, where all we do is, well, it's just once you've got the recursion, writing out the algorithm is usually very simple, right? You just write the initialization stuff at the top, and then a for loop where you fill in all the entries. And so that's what this is. It's just all of this is just initialization. And I don't even know why I've written it this way, but the first way, like the way I've done it is I start by filling them all out to infinity, and then I just loop through all my edges and I set those ones to Lij. It's the same thing as what we wrote right here, right? It's just, I start off by populating them all with infinity, and then I overwrite the ones that have a finite distance. Yeah, yeah. No, usually it's a good question, but like you don't, okay, that's a good question actually. It's kind of convention, I guess, in terms of like, you're right, in like our assignments and things like that, right? We've talked about the distance from a vertex to itself as being 0. Sometimes people also call that infinity. So I guess here we're using the convention that it's infinity, but you're right. Maybe I should have said dist I0 is 0 just because it's from a vertex to itself. I think this is the way it's written in the textbook. It's actually a very good question though, or a good observation. Basically, I mean, just to, say one more thing. It won't affect anything. The only difference is when you output this matrix, whether along the diagonal, there's going to be infinities or there'll be zeros. That's all it'll change. It won't change any of the off diagonal entries, the true like dist from I to J. And then this part now you can see is like this triple nested for loop, right? Where I have to loop over K on the outside. And then when I fix the value of K, I have to compute all pairs shortest paths, right? So from all I to all J. And so we can see that this part's going to cost me order n cubed time, right? Inside, I'm just taking a min of 2 values. And so the overall runtime is big O b cubed, or where, cardinality of V is n. Big O n cubed. Which, if we go back, we've saved a bit, right? We've got V cubed here. And let me just quickly scroll up. In this one, we got E times V squared. E times V squared. So if E is bigger than V, then our new algorithm does better. This could be as bad as V to the power 4, right? So, okay, let's stop there. Sorry that went a little longer. I just thought it's awkward to end with 5 minutes, then to talk after the break. Let's take I don't know, we can come back in 7 minutes or something like that and continue. So in this course, there's 10 chapters in total, and we're on to 8. So we're doing well. This is actually a fairly short one, I would say. Then the next one is going to be on complexity, like P versus NP and NP completeness and things, which are maybe terms you've heard of or not, but it's a pretty interesting component. And that one's kind of long. And then we have a final shorter chapter, chapter 10, on how do you solve these hard problems. Yeah.
Sorry, so quick question. Next week, March 16th is the setup date for that.
I don't know. Yeah, I haven't gotten an email about that. I thought that the symposium was on Friday, or is it Thursday?
Thursday.
Thursday, I see. But Wednesday is a setup day.
Yeah.
Maybe I'll wait to see if I get some guidance. I mean, in the worst case, I'll record. I mean, I'll be recording the lecture so you can watch it after. But I'll just see. Usually, we get an email that tells us what we're supposed to do for that week. I was kind of like my goal, or not goal, but what I was sort of hoping to do is basically finish by the 12th week, so that we have that final lecture on the Tuesday of like kind of week 13. That's the very last day of class. I was hoping to be done by then, so that we don't use that one, or we just like, just go over some review briefly or something, but no more content. So that's sort of my one constraint, right? Is if I skip. If we're skipping them, for sure, like I will. I'm not going to like run it if it's being canceled. It's just, if the lecture's still there, I might cover material that day, just to. Also, because our exam's on the 11th, so I'd rather finish covering things a bit earlier if possible, to give a bit more time for studying and stuff. But anyway, so linear programming. This problem feels a little different, but it's a very useful tool that I think, even as you go out into the world, like working, whatever you're doing, you might just want to like have this idea on your radar, because if you're encountering a problem and it turns out it can be solved with linear programming, there's a very nice way to do it. And there's like very well developed tools, packages, and whatever language you're programming in to solve linear programs. And the next assignment will get you to use like one that's built into Python for solving linear programs. But so this is kind of a high level overview. We're going to go into, I mean, you'll be able to understand some details of it, but I want you to be aware of linear programming. So what is linear programming? You're given a set of variables. Now they're variables, and you can assign real values to them. And you have a set of linear equations or inequalities that have to be satisfied by your variable assignments. And you want to minimize or maximize an objective function. Okay, sounds a little abstract. Let's give an example, like a toy example, but where we can write out a linear program. So let's say you or me, we run a factory and we sell 2 products. Product 1 sells for $1, product 2 sells for $6 a piece. We also know the maximum demand for product 1 is 200 a day. The maximum demand for product 2 is 300 a day. And our factory can produce at most 400 products per day between P1 and P2. And our goal is to maximize, let's say, revenue. So just maximize the sum of the dollars that we would receive for selling our products. So this sounds like a high school or grade school like problem, although it's got a few constraints, right? And an objective. So let's write out this problem, like what it looks like. I'm going to define x1 to be the number of product 1 that I produce, and x2 to be the quantity of product 2 that I produced. So if that's my definition, then I want to maximize I get $1 for each P1 and I get $6 for each P2. Right, so I want to maximize X1 plus 6X2, subject to several constraints. So I'll write such that or subject to. And what are my constraints? I know that there's no point making more than 200 units of product one because that's the demand. Right, so X1 should be less than or equal to 200. Product 2, I can make at most 300. X2 is less than or equal to 300. And combined, I can make at most 400 products, right? So X1 plus X2 has to be less than or equal to 400. And I know I can't make a negative number of either product. So X1 and X2 have to be greater than or equal to 0. So that's a linear program. That's what I meant by, right? Like our goal is to assign values to X1 and X2 such that we satisfy all those constraints and we maximize that linear objective function. It's called linear programming because all of our equations or inequalities are linear in the variables X1 and X2. And it's by design that I'm showing you one that only has 2 variables. It's because I can nicely plot this problem and we can visualize what it looks like. And it'll give us some insight into the problem in general. So we can plot the constraints which defines a feasible region in the X1, X2 plane. Right? Feasible region just means the set of all X1 and X2 that satisfy all of my constraints. So let's try and draw this. So I draw a vertical axis and a horizontal axis. Let's say that this one is X1, this one is X2. So let's say this is 100, 200, and then on the vertical axis, 100, 200, 300, maybe. 300. And so what are my constraints? I have the constraint that X1 has to be less than or equal to 200. Right, that's this one. I have the constraint that X2 has to be less than or equal to 300. Well, close enough to being on 300. That's this one. And then I have the constraint that X1 plus X2 has to be less than or equal to 400. So if I draw that line, it should pass through 400, 0, and 0, 400. Or, I mean, it also will pass through the point 100, 300, and it'll pass through the point 200, 200, right? So it's that line. Let's try that one more time. All right, good enough. Whatever. And then my feasible region is like all this stuff in here. Right, that's where I'm on the correct side of each of my constraints. I guess the one other thing, right, is I also had the constraints that X1 had to be greater than or equal to 0 and X2 had to be greater than or equal to 0. And one thing you notice is that that feasible region that I've drawn is a convex set. So what it means for that set to be convex is that if I take any 2 points inside that set and I draw the straight line connecting them, then the entire line also lies in the set. So notice that the feasible region is convex. The line connecting any 2 points in the region also lies in the region. That's the definition of convexity. So let me just draw something that's not convex. Right, that set is not convex because if I take, let's say, these 2 points and I draw the line connecting them, the line goes outside of the set. And like that little notch sometimes is called a non-convexity, right, in that set. Okay. The other thing that's interesting to draw on my figure up there, and I'll scroll back up to it in a second, are lines of constant objective value. So our objective was x1 plus 6x2. And so we can draw like the set of all points where the objective is constant. So it's the line x1 plus 6x2 equals a constant. So let's, for example, draw the line x1 plus 6x2 equals a constant. For example, C equals 1200. So let's go back up to the line. So I want to now draw the line x1 plus 6x2 equals 1200. We know that that's a line that passes through when x2 is 200, then 6x2 is 1200, right? And x1 is 0 there. And then on the other side, when x1 is 200, then x2 has to fill in the remaining 1000, right? So 6 times x2 has to be 1000. So x2 there has to be like 166, something like that. So it's going to pass through like right here maybe. And then this is my, we could call this my profit line or my revenue line. Try one more time. This is the line x1 plus 6x2 equals 1200. And what I can think of doing to find the optimal value, I can think of moving that blue line upward until it just stops touching the feasible region. And the last place it touches the feasible region should be the optimal solution, because that's the, right? These are all the points where I get an objective value of 1200. If I move it up a bit, it'll be like all the points where I get an objective value of 1300. And so the last point it touches will be the optimal solution. So as I move it up, it stays parallel to one another. What's the last point that gets touched in the region? Yeah. Yeah, it's that pink, purple, whatever color on the green line there. So that last point is right here. That's going to be the last point I touch in the feasible region. So if we move this line up, i.e. x1 plus 6x2 equals constant for increasing C, the optimal solution is the last point in the feasible region that it touches. And you can see that in this case, it lies at what we'd call a vertex of the feasible region, right? Like not on one of the edges, but at the vertex. And that's not just by chance. This is actually a property of linear programming, that in general, the solution will lie at a vertex of the feasible region. So in this case, the solution is x1 equals 100, x2 equals 300. And okay, this problem is it's a toy example, right? It makes perfect sense, the solution. If you go back up, like just ignoring all the mathematics for a moment, I got $6 for each product 2 that I could make, and I can make at most 300. So of course, make 300 of them, right? They're worth way more. And then I just fill in the gap. I'm only allowed to make 400 in total. So that means I still have 100 capacity left. Make product 1 with that, right? So that's why I get the solution 300, 100. But we're building up a kind of general insight about this problem, not this specific example. And so this is a general rule. The optimal solution lies at a vertex of the feasible region. And the only exceptions, yeah.
Actually, maybe
Yeah. So it still lies at a vertex. It's just not unique then, right? It actually, like, yeah, like the 2 ends are valid solutions, but like I think the question is, if I made this blue line perfectly horizontal, let's say, then it would touch the whole green edge up there, right? And every point on that green edge at the top would be an optimal solution. But it doesn't contradict what I'm saying. Still, a vertex is an optimal solution. It's just now it's not unique. Yeah. Up at the top one, or? So the blue line I'm plotting for 1200, I think where it hits the big blue dot up at the top, that'll be an objective value of 1900. Is that what you're asking, or? Oh, I made it up. Yeah, totally arbitrary. I was just trying to show, a point where I knew it would lie inside the feasible region still. Yeah. Okay, so the only times where the only issues can be when the problem isn't well defined. And so there's 2 ways it can be not well defined. One is that my feasible region is empty. And for that, we say it's infeasible. It's not possible to satisfy all the constraints. It's easy to come up with examples of that. Like, for example, let's say I have the constraint that x1 has to be less than or equal to 3, and then I also have the constraint that x1 has to be greater than or equal to 4. And no assignment of x1 satisfies both. And the other one is that the linear program, or LP, can be unbounded, which just means I can keep increasing my variables and get larger and larger objective value. And so a simple example of that would be something like, let's say my objective is maximize x1 plus x2, and my constraint is that x1 plus x2 be greater than or equal to 0. Then I can just make x1 and x2 1 billion, right? And I get an objective value of 1 billion, and so on. Or set them to infinity. So if these 2 cases, if the linear program is feasible and it's bounded, then the optimal solution lies at a vertex, or an optimal solution lies at the vertex. And so now what we really think of doing is we have to find an algorithm to search vertices of the feasible region, right? That's how we're going to find the optimal solution. And the idea is pretty simple. So this is like the first algorithm that was, or like first main algorithm that was developed for solving linear programs. It's called the Simplex method. And the description is dead simple. The implementation, not so much, but the description is really easy. So start at a vertex, arbitrarily, just find one. We'll talk about how to do that. And then look for an adjacent vertex. That means one that shares an edge, right, on the feasible region. that has a better objective value. Move to it and repeat. And when I get stuck, when I get to a vertex such that none of its neighbors have a better objective value, output that as my solution. So repeat until no better vertex exists. Now, why does that work? Let's see if I can steal this thing. Okay. So first, let me just draw the algorithm. So what I would do, start at a vertex. This has an objective value of $0. And now I move to a neighbor that has a higher objective value. There's two neighbors, right? 0, 300, and 200, 0. I don't know, pick one arbitrarily. I'm gonna move this way. And then I get to here. Now I get a value of 200. Now there's only one unvisited neighbor, which takes me up to this point, which is the point of 200 in x2. So I get 1200 plus 200, 1400 in total. And then I go along here and I get up to this point, which is the 100, 300 point that gets me 1900, I think, right? And so that path is like my simplex algorithms path to get to the optimal vertex. Now, why does this find the optimal vertex? Why is it true that what I'm claiming basically is that if I can find a vertex where all of its neighbors have lesser objective value, then I'm at the optimal. Right? That's the claim. I mean, if that's not true, then this algorithm is incorrect. And it takes a minute to think about it. So you can kind of picture it in this, maybe let me draw here. So here's the profit line, right? So when I get to this point and the profit line looks like that, I can see that both of my neighbors are below the profit line. And since both of my neighbors are below the profit line and the feasible region is convex, it can't have any of those non-convexities, the region can never go back above the profit line. The only way it could do that is if it went non-convex, right? Somewhere like it tilted back upward. And so it's kind of easy to see in 2 dimensions, but this holds in general that once I find a vertex where all of its neighbors lie below that kind of profit line, then the entire feasible region has to lie below the profit line. So why is the feasible region, or why is this point optimal? Because the feasible region is convex. And let me just fill this part in and then we will stop. So if we reach a vertex such that no neighbors have better value, then all neighbors are below the profit line or revenue line, I don't know, passing through that vertex. And then convex implies entire feasible region lies below that line. And this has nothing special to do with the profit line. It's just if you take a convex set and you draw a line that touches that convex set at only one point, then necessarily the entire convex set has to lie on one side of that line. Because the only way it could cross back over the line is for it to like go something like that, right? Like a bean shape or something, but then that's not convex. Okay, so let's stop there. We'll continue with linear programming tomorrow.